My name is Robin Getz, and I'm an engineering manager in Analog Devices. Today we're going to talk a little bit about integrated software-defined radios. This is a list of things our lawyers make us say. Today's agenda will be looking at, software-defined radio, a little bit about it, a little bit about the history, some of the math behind SDRs, how to solve channel impairments, and various solutions for SDRs, including the FMC Comms1 board, which encompasses not just the hardware, but the tools, drivers, and actually even HDL designs. What is a software-defined radio? A software-defined radio is typically thought of as some type of communications system where components have been implemented in software or HDL on an embedded computer, an FPGA, SoC, or combination like the Xilinx Zynq. The concept of SDR is not new. It was actually developed around the early 1970s. However, then many of the techniques which were only theoretical possible, where people had concepts and ideas, weren't actually being able to be implemented just because the electronics did not exist at that point in time. Now, things have actually progressed from a digital electronics perspective, where people can actually do things and have them real-world implementable at a price point that people can ship a real system at. So, why SDR? SDR makes RF hardware much, much easier. It's much easier to add new features since they're all in either software or HDL or some kind of other programmable device. And it's easier to have one set of hardware handle multiple modulation techniques. It's also easier from a lower cost, lower risk, lower BOM systems to have one RF platform handle multiple different solutions. So here we have an example of an SDR type of platform where we have all of our analog electronics, our DAC, IQ on the DAC, going out to a modulator, going out to gain blocks and potentially optional front end for gain, receive path, optional LNA, demodulator, VGA, ADC that gives us IQ, which is either fed from the transmit side or received on the receive side from a digital logic inside our FPGA or our, like I said before, processing system. As well as on this platform, we need to have, clock generators, synchronizers, dejittering devices, distribution, and our LO frequency synthesizers. So our radio that we looked at before was a direct conversion radio, and these are known by many different names: Homodyne, Synchrodyne, Zero IF. All of these describe the same basic kind of topology, which is a transceiver design that demodulates or modulates the radio signal using a local oscillator or an LO whose frequency is identical to or very close to the carrier frequency of the intended signal. So, we have it's very attractive due to the simplicity of the signal path, suitable for very high levels of integration, and allows very wide bandwidth of designs. The design that we have in the FMC Comms1 has over 125 megahertz of channel bandwidth and receive capabilities from an RF standpoint from 400 megahertz to 4 gigahertz, which is hugely wide. Some of the transmitter advantages and challenges, it's very low component count, leads to very low system cost, power consumption. The direct up conversion produces very or few mixing spurs and requires typically much fewer filters if you had than multiple IF kind of stages. During the challenges of some of these, or during the modulation process, gain and phase mismatches of IQ signals will have an impact on sideband suppression performance, which we'll talk about later in the presentation. One of the other big challenges is the out-of-band transmissions, either LO or carrier leakage or IQ mismatch causing images of the output spectrum, and we'll also talk about this and some of the things where these come from and how to get rid of them. Some more kind of advantages, challenges, or, low component costs lead to lower system cost. There's much decreased need for image rejection filters. Filtering requirements are much more relaxed at the baseband. And, fewer gain stages at the baseband require or provide much better power savings. The challenges are these DC offset appearing at the baseband, the self-mixing, offset voltage problems, which we'll talk about again. Images appearing symmetrically around the zero frequency from IQ mismatches in phase and amplitude, and even order nonlinearities where, two high-frequency interferers close to the channel of interest can result in these nonlinearities that fall into the band of interest. So, how do these actually, where's all this I and Q come from? For this, we need to go kind of back to Euler's formula, where we have our two signals, our sine and our cosine signals. When we look at the complex values of these, you can see that, sine and cos are really the e to the omega naught t plus e to the negative j omega naught t, and the sine is just a little bit different in terms that we have our instead of a plus, we have a minus in the e to the negative j. And when we add these together, we can see that they mostly cancel out. So we have a sine plus cos is really just the real side of the image, where sine is exactly 90 degrees out of phase with respect to cos. And when we have perfect amplitude match and perfect phase match, the signal content at that omega naught actually cancels, or negative omega naught actually cancels. Now, the problem is that in most systems, we can't ever have perfect amplitude matches and perfect phase matches. So what does that actually cause? And as we work our way through the math, we can see this, it actually causes these images to pop up where we shouldn't have images. And in an RF system, these cause signals to be broadcasted in channels that we shouldn't be broadcasting in, which won't maybe affect us, but it'll affect other systems or other radios we're trying to communicate in that band. So this is typically measured by EVM, or error vector magnitude. So when we're talking about these higher level modulation schemes like 16 QAM, 64 QAM, 256, where we have our desired or our ideal signal and the actual signal, we can actually measure this as a percentage where we have noise and imperfections cause these displacements from ideal locations, and these large EVMs result in symbol errors or degraded bit error rates. So to try and kind of get an idea of what this actually means, if we just look at QAM or a QPSK signal, which is four dots in our IQ kind of path, where we have our 10% kind of quadrature gain errors, we can see that we have kind of an offset. We have a 1% quadrature offset error. Things are shifted to the right, and we have a phase error. The constellation actually looks twisted. So we can see that these constellations can actually cause bit error rates, or these problems in the constellation can cause bit error rates if the EVM is actually too high. So we can actually see around over here that our bits are supposed to be all inside the square, and these few bits that are actually outside the square, when they should be over here, are going to actually be up in the middle, which is going to cause us a problem. So, where does it actually come from? The effects of this IQ mismatch that we were talking about before that causes this, either gain error or phase error, or desired images or undesired images can be all accounted to these, gain errors and phase errors. So we can see that these effects of IQ mismatch, or these gain errors and phase errors, are going to cause EVM degradation as our actual constellation points move away from our ideal locations. The other thing they can do is they can actually cause our interference with other desired signals that may be in other bands. So we can see here where our desired signal right here at F1 is aliasing back to minus F0, which is causing a different radio's desired signal to be swamped out, which isn't good for that other radio. So here we look at our direct conversion transmitter architecture, which includes our DAC, our modulator, our gain blocks, and potentially our power amp, and trying to figure out where these IQ mismatches or phase and offset errors actually come from. And kind of just as a quick review, we looked at these complex IF architectures using IF DACs to synthesize a intermediary frequency signal and its conjugate as the inputs to the modulator. And this makes a single sideband upconverter that rejects most normal mixing products, easing the baseband filtering requirements. These complex IF systems do, however, create several images. They create one at the FDAC minus Fout, which is the main and desired signals image, and then, potentially even harmonics, so would be the second, the third, which could be real or folded back into below the modulation carrier, below the LO frequency. Careful frequency planning must be done to avoid folded products falling too close to the desired path that are then actually upconverted. And typically post-modulation, a baseband filter is used to filter these undesired products to try and eliminate things. So we have potentially DAC termination mismatch and phase and gain in the filter, modulation input termination mismatch, or even potentially small amounts of mismatch actually coming from the ICs that can cause these kinds of problems. So these fixes for these non-ideal issues is inside the DAC itself. Inside ADI's AD9122, we actually include offset calibration, gain calibration, and phase correction. So we can actually correct for the three different things that can cause us problems: phase, gain, and offset. And here we can actually see the effect of a normal system with these three things actually set to 0. We can see here DC, or our LO leakage. We can see here our image folding back. With these three things actually tuned properly in the 9122, we can actually see our frequency that we want out, and no DC, no LO leakage, and no image. So things can actually be canceled out. So inside the 9122, we can also see that, the DAC is actually just a small portion of things when it comes to the system. We have a lot of receive, filters, and modulation that can actually happen in the digital domain before things actually get to the DAC. So what those filters, pre-modulation, NCO can actually be used for is interpolation of actually the data, so we can take a signal and actually move it around anywhere we want to in our bandwidth of the DAC itself. So we can have interpolation from 2, 4, or 8x. We can modulate the signal. We can also center shift the signal, and this actually is determined how these filters are actually programmed. What is that going to actually mean for us? So when we're doing things like doing a 8x filter, our bus bandwidth goes down, our F data goes down, and our signal bandwidth goes down too, but we still have this 1.2 megahertz or 1.2 gigahertz worth of bandwidth. We can actually put everything inside the DAC. The other thing it does mean, though, is that our power consumption in the DAC does go up as these large digital engines are turned on. And as they're not turned on, the power will go down. But it is a trade-off of power inside the DAC or power inside your FPGA or digital engine. So, why would you want to do this? A lot of the reasons to do this is actually to decrease the data rate that actually must go from the FPGA into the DAC to allow you to make easier timing requirements. Allow you to place your logic inside your FPGA a lot easier. So, it does decrease signal bandwidth, it does increase the power of the DAC, but also does decrease the power of the FPGA. So it is very much a system-level trade-off between FPGA resources and fixed processing in the DAC, which does help quite a bit with these system timing constraints on the FPGA. So if we look at an example of this, here we can see a 1x interpolation where we have our signal here, and then we can see the aliases of that signal appear from the output of the DAC. And now we can actually see a 2x interpolation, and then our images actually go out, and a 4x interpolation, and our images go out again, another double. And you can see that one of the benefits of doing this may be that our filtering requirements actually are much sloppier over here when we're doing 4x interpolation as opposed to when we do 1x. If we want to consume this bandwidth right here, doing that with 1x interpolation, we would need to have a much tighter brick wall filter. So the tighter requirements are going to mean that we need more higher order filters than we would when we're doing a 4x interpolation. So when we look at things that are doing up conversion, here we have our no up conversion. Here we have f over 2 up conversion and f over 8 up conversion, and you can see that our images are actually like separating, which also again is making things much easier to filter. And so if we combine these two pieces, we have no up conversion, we have up conversion, and 8 over 7/8 up conversion. And we see here our LO leakage, and here's the signal. And again, this is going to be much easier to filter because the filtering requirements are much sloppier. So, when are these kinds of things useful? So on our platform that we did, the first implementation that we did, the two LOs were actually fairly close together. And we didn't put tin cans on the top of things because we actually want people to probe on the PCB and get an idea of how things are acting and how things are reacting to the different signals that are going through. So our two LOs were actually very close together on the PCB. And what we found was that when the two LOs would actually interact with each other, because the loop filters were actually basically just too close on the PCB, which caused all kinds of spurs when the LO and TX PLLs were within 100 kilohertz of each other. When they were not 100 kilohertz of each other, because you could, for example, center shift the modulator or center shift the DAC, then you'd get a much better signal coming out into the LO that's going to be modulated, going up and being modulated. So in terms of receive architecture, we have essentially the same thing, just the opposite direction. We have, potentially a external LNA, DMOD, VGA, and then ADC, where we still have our cos and our sine, just like we did before. And, the imperfections of the system still exist. There's gain imbalances, phase offset voltages, imperfections in the in-phase splitter that could potentially be there. ADI tries to minimize these, and you can see that on our data sheets. We typically have less than 1 degree phase margin, and which impacts the system much less than the external components will. And this is actually where things actually dominate, is these PCB layout mismatches. We've actually seen issues where the weave of the FR4 can actually determine a lot of these phase and offset mismatches, component mismatches, offsets within the ADC or the DMOD. And in our system, we do have a VGA. Again, that is differential going through its system, but does have some mismatches there as well. Here we can see some very critical IQ demodulator specs, which is the LO to RF leakage. Here we have our LNA, going through to our DMOD, and so for example, this could be at 2.4 if we're trying to demodulate something around 2.4, and we could have some of this actually coming through and getting all the way through to the ADC. If LO leaks into the RF input or the LNA, it actually mixes or multiplies with itself in the mixer, actually generating DC offsets on top of what's actually recovered in the baseband data stream. So, these DC offsets, quadrature error corrections, can actually be implemented digitally in the receive chain. DC correction, if DC-free coding is using, a notch filter can be applied, which is some of what we do in the FMC Comms 1 platform. And we can also have quadrature error correction, where we actually calculate like an I squared minus Q squared to try and determine the power difference between I and Q, and a phase correction to actually cross-multiply I and Q, and, they should be, 0 if they're perfectly orthogonal. So, direct conversion and Homodyne receivers all have their own merits and their own challenges, but it's critically important to try and pay attention to gain, phase, and offset errors that, can be addressed with, various quadrature error correction algorithms. And some of these algorithms are actually implemented inside some of our newer continuous time sigma delta ADCs, the 9262 and the 9269, which is a dual pipeline ADC, in terms of this, automatic quadrature error correction, or QEC. From a clocking perspective, the clocks have both a dejittering device and a clock distribution part. The clock distribution part, the 9523-1, has both an on-chip PLL and an external VCO with two VCO dividers. These cascaded PLL stages are used to try and synchronize external frequency phase and frequencies up to the input stage, so we can have a single reference being driven to multiple platforms to actually be able to handle MIMO. Now, our first stage PLL consists of an integer PLL that uses an external VCXO from 15 to 250 megahertz. What we have on our platform is 122.88. And the second stage PLL is a frequency multiplying PL that translates that 122.88 to an output range of anywhere between 2.9 and 3.1 gig, which is then divided down at the outputs. And we can kind of see that here on our FMC Comms 1 clocking, where we have our DAC clocks, our ADC clocks. We have an internal VCO of 983.04 megahertz, and those are divided down to get our 491 megahertz as our DAC clock and a 245.76 megahertz ADC clock. And then we have this functionality on here, which are zero delay, where we actually take an output and feed it back through and use that in our PLL, so we can make sure that all of our outputs here remain synchronous with our input frequency. Now, some people have said that they didn't really like our selection of clocks, and you can change those around as you see fit. The current configuration is 122.88 times 24, which gives you the 2949 megahertz clocks, which divides down to 245.76. If you want to have integer functionality to get like 128.000 megasamples per second on the ADC, you could use a 3072 megahertz in your ADC or in your internal PLL2, which then can divide by 8 to get an even frequency. If you want to try and increase things to get exactly 250, the closest you can get is 249.856. It all depends on how you can set these clocks up, and they are fairly flexible. Potentially you could do these kinds of things where you have this 1024 megahertz clock here and get, DAC clocks of 128 or DAC clocks of, 1024, assuming you have an 8x interpolation inside the DAC turned on, and your ADC clock could be 128 or 64 or whatever you happen to want. However, because we do have a fixed 30.72 on the input, or a fixed 122.88 on the requirement for our VCXO, because this frequency is no longer a integer multiple of 122.88, the zero delay function no longer works, and you can't actually synchronize multiple systems together. From a power perspective, FMC as a standard provides 12 volts and 3.3 volts and an adjustable voltage. So on this system, we typically use just the 12 volts and 3.3, and those would drive the entire system. To do that, we have a couple one switcher, the ADP 2323, and then just a few LDOs on the system, from 2 amp LDOs to the smaller 150 milliamp or to 400 milliamp LDOs. So the first piece to look at is the ADP 2323, which is a very high efficiency, very small. You can see it's about the size of a dime for the entire thing. It's 24 millimeters by 21 millimeters in its most compact configuration. Optional pulse frequency modulation reduces switching losses at very light loads. And it even we don't use it on this design, but you can actually have multiple 2323s tied together to try and reduce input ripple and minimize input capacitance in the system. The solution that we have is right over here, where we have the red dot is the device, and it's a little bit more spread out because we did have a little bit of extra room on the platform that we could handle. So in terms of multi-rail applications, We do have the option to connect multiple 2323s together with the synchronization input, and that will actually ensure that all the clocks or all the switching frequencies are actually just slightly a little bit out of phase, and to try and minimize the input voltage ripple. And we can see that what happens when we don't have things can end up like beating against each other and maximizing the input ripple and maximizing the number of capacitors you'd have to add on the input to try and get the same voltage ripple. From a LDO perspective, ADI kind of leads the industry right now in terms of LDOs and high power supply rejection and the output broadband noise. So when we look at things, it's the ADP 150, 9 microvolts of RMS broadband noise, 20 nanovolts per root hertz of spectral energy at up to 100 kilohertz, and over 70 dB of power supply rejection at 10 kilohertz. And some other devices that are just sampling that weren't actually available when we designed this platform, that are actually even pushing the envelope even higher. So here we'll just have a quick look at some of our newer devices, the ADP 7102 and 7104, which are low noise performance devices, where the big thing to notice about the 7104 was the noise doesn't actually increase when the output voltage increases. So here we have the same input voltage to the device and a 3.3 volt and 5 volt outputs, and the noise spectral power density is very, very low, independent of output voltage. And the graph on the right is the 7102 and 7104, showing that no additional bypass capacitance was required. It's stable with a 1 microfarad output capacitor, where the power supply rejection does increase with frequency of the noise at load, just like all LDOs do. But has excellent settings or figures at 70 dB at a kilohertz, or 58 at 10, and still below 50 at 100 kilohertz. So when we look at the ADP 151, the 1 over F noise is superior to its competition below 100 kilohertz. Here the ADP 151 is available in the green. So here we wanted to get an idea of how good is the ADP 151 compared to the best thing that we could think of. Where the best thing that we could think of from a LDO perspective was actually just AA batteries. We compared the ADP 3334 against the ADP 151 and 2 AA batteries. So when we look at things, we actually connect that up to the output of a PLL that we actually can find on the FMC Comms 1 platform. So we can see that our previous generation device, the phase noise coming out of the PLL is directly proportional to what kind of noise it actually sees on its supply. And we can see that the 3334 LDO and from a USB supply is actually much higher, about 6 dB per hertz of phase noise from a ADP 151 or our AA batteries, which are almost identical. So we don't think we could actually get much better than this in terms of the improvements in things until we can still continue to improve our PLLs, which is always occurring. So, one of the questions that we typically get is, why did ADI try and design a SDR platform? And so, ADI has always been involved in SDR from the very get-go. We've done various things from various platforms, people connecting our eval boards up together. But when we saw people doing this, it was, kind of large and cumbersome. It's 6 power supplies and 4 USB applications, discrete single product evaluation boards all connected up with SNA cables. It wasn't very easy to replicate, and it wasn't actually very easy to use as part of a prototyping solution. So we needed kind of a small form factor open design. So we actually developed the FMC Comms 1 board, which plugs directly into a Xilinx platform. What we see here is the Avnet Z board connected up to the FMC Comms 1. So with that, you plug in HDMI, which is driven by the ADV7511, and that drives right out to the display. And then this is the GUI that you see, and you actually boot Linux on the system. So the FMC Comms 1 connected to a Vertex 6. You can kind of see here the card, the top and the bottom. It's almost an FMC form factor in terms of the width. You can actually put two of them on, and it's just a little bit longer than normal. So when we look at the entire platform, it has everything that we've been talking about. It's got our network, clock synchronization, clock distribution. It's got ADCs, it's got the DACs, it's got the modulator, demodulator, gain blocks, and VGA, as well as all the necessary power to keep everything all happy and performing as well as it can. So again, looking at our block diagram, we have a full transmit path with a 1.2 gigasample DAC, a 400 to 6 gig modulator, a 50 to 4 gig gain block, which kind of makes our transmit specs from 400 to 4 gig. And then on our receive side, we have our demodulator, our VGA, and our ADC. So from a reference design standpoint, we have HDL. They would include like microblaze-based designs in the ML605, KC705, VC707, ZC702 or ZC706 and the Z board, which are all based on either microblaze or ARM. And the software with Linux, which is our recommended solution, drivers for all the programmable parts, the 9122, the 9548, the clock devices, the PLLs, the ADCs, the VGA, streams data over the network, and has a GTK-based application for ARM-based platforms. We also provide some what we call our NoOS or basic drivers for people who don't want to use Linux. One of the key things to remember about this kind of system is that, in all these programmable devices, there's over 1,000 different SPI configuration registers, because things are very programmable. It's very agile. You can program it, and we talked before about the features inside the DACs and the ADCs and the clock devices that all need to be set up properly before everything actually can work. So what we tried to do is actually make that much easier for people by providing these HDL and Linux software and the NoOS software to make it a little bit easier for people. So we'll just talk about that for a quick second. When you look at the software kind of system architecture, and we talk about software drivers, we're talking about the device driver that hangs out over here on the Linux side, whether that be Android or just Ubuntu, which is what we typically run. You still have all your system libraries, your applications, and your application frameworks. ADI does provide both the devices and device drivers, provides the HDL, and provides a small application to actually look at things. And here's kind of that application, because you can look at things in the frequency domain, control things from the GUI, to make it a much faster out-of-the-box experience to just kind of get things running, play with it, and then you can start ripping it apart and putting your own IP and your own modulation schemes, those kinds of things, inside the FPGA or inside the ARM chip. So, in conclusion, we talked a little bit about software-defined radio, how to solve these channel impairments, solutions for the SDR, which included the FMC Comms 1 board, tools, drivers, example HDL designs, where to go to get things. We looked at a combination of these products. So here's just a quick picture of what you can see on the exhibit hall. Ubuntu Linux running on the Z board or the ZC702, FMC Comms 1 on the Zynq. We'll be able to interact with it from a HDMI display and USB keyboard mouse. And this does provide full transmit and receive, and all these things are available for purchase. So come see the demo, buy the board, buy the Avnet kit, ask questions in the engineer zone, and check out the wiki. So thanks very much for listening.